Welcome to the thermodynamics lesson on calorimetry. Calorimetry is the process of measuring the heat of chemical reactions. We'll talk more about how you do that type of calculation here in a moment. First, let's start off by taking a look at what is known as a heat graph. And to make this relate to you well, we're going to do a heat graph for H2O. And you can see that on our heat graph we have temperature on the y-axis and time is on the x-axis. And it should look familiar to you as H2O because at 0 degrees Celsius and at 100 degrees Celsius we have plateaus in the heat graph indicating to us that that is a phase change. More on that as we get through the heat graph itself and the things that we're going to label here. Okay, we'll start at the bottom. It doesn't matter, the heat graph could be on the, you can analyze it on the way up or on the way down, it doesn't matter. But what we know right here in that process right there is that the H2O is in solid form. And of course we call that ice. How do we calculate the heat that is being added to the ice or lost by the ice, depending on if you're going up or down the heat graph here? And this would require a Q equals mc delta T, where C is the specific heat of ice. So the mass of the ice, the specific heat of the ice, and the change in temperature. If you multiply those three, you get the heat that is either added or lost by the ice, depending on if you're warming it or if you're cooling it. So some people don't realize or understand that ice can be colder than the freezing point. And we've had a lot of experience with that this winter. These really cold days, that snow or ice even has a different sound to it as you walk on it. Okay. All right, moving on. We have our next process here. Here our H2O is in the process of melting, if we're on our way up the heat graph, or freezing if you're on the way down the heat graph. And what this would require, since there's no change in temperature, this is a phase change. This is a Q, still adding heat to it, equals mL calculation. And the L is the latent heat, and in this case it's the latent heat of fusion. So this would be a Q equals mLF calculation. That's how you would calculate the heat added to or lost by the H2O as it's melting or freezing. In our next stage, we're obviously increasing the temperature of the H2O, and now we've changed over to being in a liquid state. This is typically, of course, what we call water. How do we calculate the heat added or gained by the H2O during this process? We would do, again, a Q equals mc delta T, but in this case, we would be doing the specific heat of water, which we're going to use it so often we will end up remembering its value, is 4,186 joules per kilogram degrees Celsius. Now you may remember from chemistry that your specific heat of water was 4.186, but what you were doing was joules per gram degrees Celsius, and because our standard unit is kilograms, that multiplies that value by a factor of 1,000. Okay, so this is how you calculate the heat added or lost by the H2O when it's in liquid form, depending on if you're rising or falling in the heat graph. Our next stage is we're adding heat to the H2O to change its state, and this would be boiling the water if you're going up the heat graph, it would be condensing the water. If going down the heat graph, and because you're not changing because you're changing state, you're not changing the temperature. So this again would require a Q equals ml calculation. But the L this time is the latent heat of vaporization, which is not the same value as the latent heat of fusion. And this would be, of course, latent heat of vaporization is changing from a liquid to a gas or from a gas to a liquid. Okay, so that's how you calculate the heat added or lost to H2O in that phase change. Here, we're apparently the H2O is gaining temperature again, and indeed, now we have our H2O in gas form. We call that steam. And one thing you learn here is that steam can be hotter than 100 degrees Celsius, and the worst kind of burn that you could ever get would be a steam burn from super hot steam that is well above the boiling or condensing point of H2O. How will we calculate the heat gain or lost? Q equals mc delta T again, and this time we would be the specific heat of steam, so we'll just put a subscript S on our variable. These specific heats, of course, would be provided for you. I've even seen them provided for water because they're not on the reference table, though we're going to use water so often, 4186, you'll just end up remembering it. But if you ever had a calculation that required the specific heat of ice or steam or any other substance, they would provide that for you. You would not be required to memorize that. So obviously you make some connections here that whenever a substance is undergoing a phase change, it's a Q equals ml calculation, and when it's not undergoing a phase change and it's just warming or cooling, it requires a Q equals mc delta T calculation. The process of calorimetry altogether is the concept that the heat gained by a substance has to be equal to the heat lost by that substance. And this is in an enclosed environment. Consider this a conservation of energy statement. The heat gained by a substance equals the heat lost. When you do this approach for calorimetry, it's really important to remember that the change in temperature is not final minus initial as traditionally we do. The change in temperature is the big temperature minus the small temperature. Okay? So when doing a heat gain equals heat lost calculation, the change in temperature, you put the larger temperature first and subtract the smaller temperature, more or less. If you want to consider that an absolute value of the temperature change, you can think of it that way. Okay? That'll do it for our lesson on calorimetry. On the horizon, more practice with doing some calorimetry calculations.